Thanks everyone for joining today. My name is Phil Derringer from the product management team at Wherobots, joined today by Ryan Avery from our RasterFlow team. We're going to be talking today how you can use RasterFlow and the new SAM3 model to do object detection with Earth observation data. I'm going to start with a quick intro to Wherobots. At Wherobots, we're really focused on two trends within the industry. Enterprises more and more are trying to make use of spatial data, but they're facing two primary challenges. One is simply the shortage of data talent, people who are familiar with working with spatial data, doing the necessary transformations, aggregations, analysis of that data. Of over 47 million general software developers, but there are only about 1.5 million developers that have familiarity with working with spatial data and the ins and outs. And the other problem is compute and simply the processing platforms that people can use. Traditional legacy GIS solutions don't really perform well at scale. They might work for very small scale analysis, but don't give you the power to be able to bring that scale to true planetary scale analysis. And new, more modern cloud engines or cloud data warehouses are really geo-incomplete. They don't have the extent of geospatial support, whether it's fundamental geospatial data types or the types of vector and raster operations that you might want to do to be able to perform these types of analysis. And last but not least, more and more we're using LLMs, we're using agents to help us with developing these solutions, but often they aren't skilled in the real nuances of working with spatial data, performing spatial transformation, working with coordinate reference systems. There's still a need for expertise to help build solutions that are accurate and can truly perform well at this global scale. So at Wherobots, we're focused on three areas to really be the AI context engine for the physical world. Today, on the bottom left, we're going to talk about RasterFlow, which is our engine for doing planetary-scale inference. Ryan will go into details of how we're using that to power our SAM3, the SAM3 model. We also have our WherobotDB engine. This is coming from Apache Sedona. It's the most efficient spatial compute engine out there for working with vector and raster data, over 300 spatial functions built in to provide complete support for traditional spatial analysis. And last but not least, our Spatial AI Coding Assistant, which makes it easier for you to work and use the power of LLMs to work with the tools available together with our VS Code extension and our MCP server. So you can work with modern LLMs to help you accelerate your development, troubleshoot your code as you're working with the power of these two engines, both RasterFlow and WherobotDB. And it's all organized around our Wherobots cloud. So this is a hub that you can use for discovery, collaboration around data, shared data sets, models, notebooks, jobs, visualizations, and skills, all organized together so that you can collaborate and further accelerate your work as you use our compute resources. In terms of where we fit into the enterprise architecture, it's a lakehouse architecture. So you can bring Wherobots compute to the data wherever it lives, whether that's in a data lake you might have or your existing data warehouses. We can work with data across GPS signals, imagery, as we'll talk, satellite and aerial imagery, as we'll talk about today, street and building data coming from Overture or OpenStreetMap or Foursquare and others. All that can be used immediately within Wherobots. So you can discover what data is available and applicable to your use case, build repeatable spatial transformations, ETL pipelines, or analytic pipelines based on that data, and then build automation so that you can run those on a regular cadence so that you can ultimately produce geospatial outputs. Those final outputs can then be visualized and integrated with a variety of different upstream applications, whether that's you want to visualize those in Esri, Carto, Felt, and others for use within your enterprise applications. So that's a little bit about Wherobots. Today we're going to drill into RasterFlow specifically and talk about how it can be used to power object detection with SAM3. So RasterFlow is a new capability we launched the end of last year, really focused on making it easy for developers to extract insights from satellite and aerial imagery with just a few lines of code. So it's a brand new engine we've developed, built from the ground up, that's optimized for the typical patterns of pre-processing, first of all, ingesting and pre-processing satellite and aerial imagery and preparing it for the application of computer vision models. We've baked in years and decades worth of our expertise and industry expertise to make it easy for developers that are new to this space to make use of these technologies right away. So handling things like cloud cover that you might experience with Sentinel-2 imagery, or handling tiling effects if you're trying to run machine learning computer vision models at scale and you want to get nice clean output results without worrying about the tiling effects that you might have if you work on a tile by tile basis. The licensing model is built around an on-demand and low-cost inferencing model. You pay only for what you use based on the size of the AOI, the size of your area of interest, and the complexity of the model that you're trying to run. And everything's fully integrated with the rest of the Wherobots platform. So as you run these models, for instance, the SAM3 to detect specific objects, those objects are geometries that you can use within WherobotDB to do further analysis, to do refinement of those geometries, or to join them with other business context so that you can join those geometries with other business data you might have to generate the real insights that matter to your business. Just a high-level diagram of RasterFlow and the building blocks that we have. Both for models and for data sets, we have a strategy of providing curated open models and open data sets to help you get started, but also an open approach so that you can bring your own models and bring your own data sets to the platform for your specific needs. So on the model side, we'll talk about that in a second, but we have a set of curated open models, a number of them coming from the Torch Geo community that you can get started with right away. Those might be directly applicable to your business or give you an example of what's possible with the types of modern computer vision models that are out there today. Or we have a pathway to bring your own model, starting today with PyTorch models exported in the PT2 archive format. You can register those, if those are published to a Hugging Face or you have those in an S3 bucket, you can simply register those models with our platform and then use them for a large-scale inference. Similarly, on the dataset side, we have two curated open datasets that you can get started with right away. Sentinel-2, worldwide coverage, 5-day refresh. You can use that data straight away for applicable use cases where you need the refresh of Sentinel-2. Or as a representative high-resolution data set, we have built-in support for NAIP. This is a US data set funded by the USDA where they do aerial image capture of the entire continental United States at relatively high resolution. Or if you have your own imagery, maybe you have your own sources of satellite or aerial imagery, or you're doing your own drone capture, you can also bring those data sets to the platform. If you have a bucket of COGs, for instance, cloud optimized geotiffs, you can provide an index to those COGs, reference that with the platform, and then you can use those data sets as inputs to any of the workflows within RasterFlow. Then we have these building blocks to help you pre-process and prepare that imagery for inference, run inference, and post-process the results. So on the ingestion and preparation side, we have standard workflows for you to ingest, composite, and build mosaics. So you can build a nice, seamless wall-to-wall mosaic from your input imagery that then is analytics ready or inference ready so that you can get the optimal results when you run your computer vision model. We then have our distributed inference engine, which parallelizes the operation as much as possible based on the model that you want to run across that seamless wall-to-wall mosaic. So you get nice, clean output results without the edge effects that you might get if you just were to run this computer vision model on a tile-by-tile basis. And you see the predicted outputs. In this case, for instance, we're seeing predicted sidewalks that have been detected in a campus environment. And then last but not least, you can use those outputs directly within the rest of WherobotDB and the Wherobots cloud. So if you want to post-process, clean up some of those geometries to build, for instance, a topology of the network of the sidewalks on that specific campus environment, you can use the standard tools we have with working with geometries to simplify them, to reduce the complexity, or to connect missing links so that you have ultimately usable and functional geometries at the end stage of this output that you can use with your downstream applications. So those are the high level building blocks. Just a few more details about the data sets and models that we have built in. So as I mentioned, Sentinel-2 used commonly in a lot of computer vision models, relatively low resolution, 10 meters to 20 meter resolution, but you have the benefits of 5-day revisitation. You also have some of the complexity because this will often include cloud cover depending on the weather as it's capturing those images from around the world. You will need to have pipelines like we have within RasterFlow to help you process and eliminate cloud cover as possible, or build composites so you get a nice cloud-free image that you can use for your downstream inference. And then we also have NAIP, representative the image here of NAIP, about 30 centimeter resolution. That's possible. This is a program basically on a 2-year basis. They fly planes around different regions of the country, capturing with aerial imagery, cloud-free imagery at up to 30 centimeter resolution. So this provides a nice high resolution data set that you can use for testing high resolution models like we'll be using here with the SAM3 demo later today. And of course, you can also, if you have your own raster data or other data sets that we don't currently support, you can bring those in as well by defining a tile index and loading that into RasterFlow. We have sample notebooks to show you the process for working with your own raster imagery. And last but not least, the models. So we have a set of built-in models, again, to provide you with examples of what's possible with these types of models when you're running it against this type of imagery. Today, we'll be talking a lot about how we can do object detection using segment anything 3 or SAM3 coming from Meta. But we also have built-in models for detecting agricultural fields. So the fields of the world model that we've talked about in previous webinars that predicts where the actual agricultural field boundaries are around the world based on Sentinel-2 imagery. Or if you want to predict the canopy height, the height of the tree canopy using Meta's canopy height model, or find roads in rural environments using Chesapeake RSC, or sidewalks, for instance, using our tile-to-net model. Those are all built in. We have sample recipes that you can use encapsulated into notebooks. So just running the cells in the notebooks, you can instantly get results to see how well these models are performing for your area of interest, to see how well they work. And we also similarly have a documented pathway for bringing your own PyTorch model. There's a solution notebook that walks you through the steps to bring your own PyTorch model to the platform and then run it at scale. All right, that concludes my brief intro. Before we move over to Ryan, I'm just going to run a quick survey question here. I want to ask in general about people's experience. And yes, I hope you should see the poll now. So yeah, we just want to get a feel for the audience and your experience with these types of Earth observation and remote sensing use cases. So we'll sit here for a bit to see the results coming in. Cool. So it looks like a good mix. About 20% are new to this area. About 30% are in production already with existing workflows. That's great to see. And then about half are in the middle, trying things out, seeing what's possible today. So, okay. Looks good. Let's end the poll. And now we'll switch over. Oh, sorry. Let me share the results out. I didn't realize you guys might not see them. There you see the final results. About 54% are exploring and prototyping with 31% already in production. Cool. All right, with that, I'm going to stop sharing and we'll switch over to Ryan to show you the demo.
Hey everyone, I'm Ryan, machine learning engineer at Wherobots, and we're going to show you a preview of running SAM3 on 30 centimeter imagery from the National Agricultural Imagery Program, NAIP. And we'll walk through also just a little bit of history of the segment anything family of models and kind of where they started and what improvements we've seen with SAM3 that have translated really well to overhead imagery. So I saw that there are some new folks who are unfamiliar with Earth observation imagery, some folks who are evaluating what's possible. So just to walk through a little bit of history, we didn't always have models that can go directly from text prompt to features detected in imagery. And so segment anything one was a big deal. Before segment anything one, models were typically trained to only segment particular categories. It only works for detecting buses or animals. And so segment anything one introduced a new task called promptable visual segmentation, which allowed you to do panoptic segmentation across an entire scene. And so you see here that segment anything one is detecting objects at very different spatial scales, shapes, textures, including trees, buildings, etc. But segment anything one has a limitation in that it doesn't assign labels to these detections. So, you can't automatically, determine that this is an emu, for example, or a person. You still have to have a human closely in the loop, labeling these detections. So while this is great for generalizing this ability to segment, um, there's still work to be done, and so future iterations of SAM have addressed this. We can also see that with SAM 1, the segments that it's generating in overhead imagery vary a lot in quality from natural scenes. And so this was me experimenting with SAM1 many years ago, seeing what segments does it detect in a small rural area in Nigeria. And it doesn't pick out any road segments, like it misses this big road. It does segment some buildings, some neighborhoods, but it's very variable what it's actually picking up. SAM 2 improved the accuracy. It added video support, but you still had to have a human in the loop actually labeling these segments. So what do these segments actually mean? So now come to SAM 3, and we now have the capability to prompt with text, with short, simple noun phrases or single words, what we want to detect in a scene. And so here you see in this architecture diagram, we pass in a penguin, or we can pass in an image example of what we want to segment. And either an image encoder or a text encoder embeds this request and passes it to a detector that then segments in imagery. It could be a different image than the input image here, where the exemplar is taken. We get to count and segment the penguins, which is really cool. And they're all labeled. So, and we don't just get an understanding of how many penguin pixels there are in the scene, but we actually segment the instances. We get to count how many penguins there are in the scene. So in remote sensing and Earth observation, a really popular task is semantic segmentation, where every pixel gets a label. Segment anything is going further by not just giving every pixel a category label, but every pixel also gets an instance label. So what object does it belong to, which allows you to count features, which is useful. And so now we can see performance for SAM3 for detecting roofs in NAIP imagery here in this example. It's really great. It's picking out a lot of small roofs, a lot of larger roofs from homes, from industrial buildings. And we're able to count these, and this can lead to many useful downstream analyses. And just compare kind of this scene from what we saw above, where SAM1 is much more spotty in picking out these roofs, and we're not able to actually determine what's the category with each of these segments. So this is kind of the main improvements from SAM3. It's more performant in overhead imagery specifically. It's one of the, I think, most capable text promptable models out there that goes straight from text prompt to detection. And this is because SAM3 was partially trained on overhead imagery domains. Um, so what we're going to show here in this notebook is some examples of running RasterFlow to really connect SAM3 to overhead imagery. So before we can even like start running predictions, we have to have a mosaic, which is a stitched together image of many scenes that have been acquired from aerial imagery in the NAIP program. So these scenes come in individual files. Um, they only span, like a strip that an airplane flew. And so we need to stitch together these many scenes that have been acquired from different acquisitions at different dates with varying quality. Maybe there's cloud cover, etc. And so that's part of what we're handling with RasterFlow is making Earth observation imagery that's acquired at different times of varying quality, making it ML ready, ready to run inference. So we're going to go over two tasks we ran with RasterFlow: build GTI mosaic, which outputs a cloud optimized format that's called ZAR, which is really useful for it's a self-describing format. So with ZAR, you can inspect easily the extent of your imagery. What area does it cover? It's well partitioned. You're able to flexibly partition ZAR depending on what sort of task you want to do, whether it's visualization or batch inference. And so that's why we're using ZAR here. And the total output size of this mosaic is 130 gigabytes. So not small. We've created this mosaic for Marion County in Oregon. And NAIP is 30 centimeter imagery. So this is fairly high resolution, which is why we're seeing this output size. If you're running inference on Sentinel-2 or Landsat, this would be orders of magnitude smaller. And so this is the power of RasterFlow. You can use it for both high resolution imagery or coarser res imagery. Um, and then the next task we're going to run is predict mosaic geometries. And we're going to predict SAM3 detections like roofs, roads, etc. in GeoParquet. And we can get a sense of how much that reduces the size of outputs you need to work with when you're trying to then get to insights from these detections. Cool. So this is what the first workflow looks like, building the mosaic. We're going to pass in an index of all the NAIP scenes, which are hosted by the AWS Open Data Program in cloud optimized GeoTIFF format. So this is a GeoParquet that indexes all of those COG files. We're then going to pass in an area of interest for where do we want to build this mosaic. So we have a single geometry describing our county boundary, Marion County Parquet. We're going to also say what bands do we want in the mosaic. So we could selectively build this mosaic just to have RGB. We can also include near infrared because these NAIP scenes also contain infrared. And we're only going to use the RGB portion when we actually go to running inference. There's some other configurations you can specify, like if you want to reproject these scenes and use a different coordinate reference system, or if you want to, supply a query to restrict what scenes can go into the mosaic. So NAIP is actually acquired at multiple resolutions. So we're going to specify that we want the highest resolution, 30 centimeter. You could change this to 60 centimeter as well. I think the NAIP program also captures 1 meter imagery. And then you can also specify a time filter. So we're selecting scenes that fall between start of 2022 and end of 2022. Um, we also support getting scenes from requester pays buckets or open data buckets. So these COGs that are indexed here are in a requester pays bucket. And so when you run this workflow, what's happening is, we're going and stitching together those scenes, etc., and doing this really performantly and scaling out. Depending on how large your scenes are, you can select different run times based on how large your area of interest is, how high resolution the imagery is. Um, and then because we run this with RasterFlow, um, this is actually run with a workflow orchestrator, and so results are cached. And so if you've already run something, there's a lifecycle policy attached to that, and subsequent runs just fetch what you cached. And so we see this here. We run this again. It takes 2 seconds. Originally, this took like 11 minutes to build this mosaic. And so that's our first step complete. We have our NAIP mosaic, and we're now ready to run inference with that. And so then we run predict mosaic geometries, our second task. We specify the output mosaic that we created in the previous step, which is hosted in an open data bucket, so anyone can go and inspect this ZAR. We'll show you soon how we can visualize this. We also specify the SAM3 model. We've actually open sourced this, so we did the work of converting the SAM3 source code, which is public on GitHub, published by Meta, into one full end-to-end pipeline in a model artifact that anyone can pull and simply rely on PyTorch to run. You don't need to install the SAM3 dependencies, and it's not packaged in a nice Python package. So this kind of helps easily run SAM3 if you want to just go pull this model down from Hugging Face and test it locally. And so then some other arguments we're configuring. This mosaic, we specified a chunk size of 1024 by 1024. And so this is the partitioning unit of the mosaic that we use for data loading. This patch size determines the unit that is going to be used for predicting on. And so we slice out 1008 by 1008 patches. This is a patch size that if you go and look at the SAM3 GitHub repo, they recommend as the optimal size because this is what the model was trained on. We then specify some other parameters like the features we want to select. We're not going to inference on a near infrared band because SAM3 expects RGB. We're going to run on a GPU accelerator, so we'll specify CUDA instead of CPU. SAM3 requires a GPU to run. We're going to specify a lot of labels to predict. The really cool thing about SAM3 is like you can specify one or more text prompts. And these can be, single words or short noun phrases. The runtime of this will scale with the number of detections that are predicted. So more prompts typically will lead to more detections. So that's something you can expect if you're just detecting roofs, for example, this will run a lot faster than if you detect all of these labels. And the runtime for this was about 40 minutes. Cool. And yeah, we're going to specify an actor, which is what is actually the uh, inf part of the inference engine that is going to run this model. It's typically um, uh, detection problem specific. So we have actors for semantic segmentation. We have actors for regression. We have actors that go from text to vector geometries, or maybe you only want the bounding box output from SAM. And so then we have an actor for text to bounding boxes. And so you get to pick and choose what inference result do you want and select a corresponding actor and a corresponding model to solve that problem. Um, yeah, some other, finally, like I guess the most important parameter to touch on here is confidence threshold. So we're just selecting the confidence threshold of 0.5. And so all detections we get back are going to be above this confidence threshold. And then you can subsequently do more specific filters with WherobotDB if you want to. Okay, and so we run this, and then what we get, we can flip over to this upcoming RasterFlow visualization tool. Um, that allows you to visualize any cloud optimized raster or vector format, PN tiles, GeoParquet, ZAR, um, and we can inspect the SAM3 results on top of our NAIP mosaic. And so I'll quickly flip over to that. So here, we're plotting our SAM3 detections on the NAIP mosaic, and we can see that it's picking out roofs pretty well, as we showed before. We can toggle roofs off, and we can see how it does at segmenting roads. A lot better than SAM1 did. Um, and we can see it's capturing like major highways, some like smaller roads in the countryside, city streets as well. And there are notably, we should call out some gaps. Like it's not always capturing roads, maybe due to shadows, um, also possibly due to predictions at the edges of scenes. And so, an upcoming improvement we want to make to how we run SAM3, which we already have for many other actor types besides text to geometries, is running predictions with overlapping patches so that we can handle edge effects. Because we've noticed that detections, um, whether it's semantic segmentation, regression, or bounding box detection, um, often you'll have some gaps at the edges of scenes. And so I expect that's what's happening here. We can also toggle off roads and roofs, and we can look at how does SAM3 do on a much tougher category, like shipping containers. And so we can like zoom into this Nate mosaic here and see in this transit lot, we see like a lot of shipping containers sitting parked. So we can see that SAM3 actually picks out some of these, which I was actually surprised by, and it's it's quite a more specific category than something like roofs and roads. But we should call out that it doesn't pick out everything. There are definitely a lot of shipping containers missed here. Um, it'd be interesting to see if we adjusted the confidence score lower than zero point 0.5, what we get. Um, and we should note that I've looked at other parts of this Nate mosaic, and it'll sometimes confuse like small roofs with shipping containers. But kind of interesting and kind of encouraging to see these promptable vision models do better on really specific categories like this. And I expect this to only get better with time. Okay, so moving back, um, once we have these detections, um, in GeoParquet and we've like filtered around, what are some other things we might want to do? We probably want to like query and like count, how many detections we get. Maybe we want to measure roof area. What's the average roof area in a region? These are some questions we can answer with WherobotDB now. So we've done that here. We've started a Sedona context to execute WherobotDB queries. And we're taking our detections from SAM3, and we can see the schema of those detections. We have a geometry column, which is what we're plotting before. We have labels, so for our categories, which are the same as what we passed in here, labels. Um, every detection gets a score, bounding box score for the object. And there's some other metadata like the timestamp for that object, which you could do to craft your own like change detection query to see, what objects changed between different dates. You can totally craft your own change detection pipeline in WherobotDB using SAM3 detections. Um, and the source is our store that each detection came from. Um, so we can like go and show what that table looks like. And this is the schema we were looking at and some detections we're getting with SAM3. And something to just call out is that these scores I feel like have a better range from inspecting different categories. Um, the confidence score is, closer to zero point 0.9 and feels more informative than previous SAM3 generations, which is really helpful when making decisions on what your confidence threshold should be for a particular category or multiple categories, if you ran multiple categories in a single run. We can detect or we can measure the area of all of our roofs using WherobotDB. So I actually used our Wherobots MCP server connected to VS Code to generate this query in the notebook. Um, and so you can kind of see some of my chat history here. Um, and we can see that what is the total area of square kilometers estimated. We're using area spheroid because our detections are in EPSG 4326, which means they're in latitude, longitude coordinates. And so area spheroid is a good function to handle that. Um, and we can then run some aggregations on this as well. So once we have areas for every single roof, we can, get what is the medium roof square meter estimate or the average. How we can also just count how many roofs we have. And so our results are down here. I also had the Wherobots MCP calculate, how many label counts do we have across all of our label categories. And once we've, analyzed our data and like we're ready to maybe generate a more snappy visualization, we can use WherobotDB to generate web optimized uh, vectors in PM tiles format. And so if we browse around, you might see that, okay, this GeoParquet is useful for selecting different categories, but it's not the best format for quickly browsing around. You can see there's some stutter and like how vectors are loaded. And this is just a fact coming from that. GeoParquet is not the best web optimized visualization format. So contrast that with PM tiles we generated with Wherobots, and with Breeze just panning around across many, many more vectors um, and getting much more snappy performance in this visualization dashboard. Um, yeah, I guess, yeah, not to talk too long, we'll just kind of cap it off with some final thoughts on SAM3, and then maybe we can go to some poll questions. Um, where SAM3 succeeds, it does really good on some categories that I would say are less niche, like roofs and roads. Um, and there's some positive improvements compared to previous generations on much more niche categories like tractors. Like we tried this out detecting tractors. Ooh, I can't zoom in, it looks like. But you can see in this image right here, it picks out two tractors in a field and misses one of them. And for some park tractors, it gets some here. Um, but there's definitely the recall for these more niche concepts is not as good. And so I expect there to be more improvement here as folks fine-tune SAM or uh, next generations of these promptable vision models are released. Um, yeah, some next things to try on where SAM3 with Wherobots. Maybe you could try and find and count vehicles that are a certain color. I found SAM3 to actually do a really good job if I ask it to detect red cars in a parking lot. It'll actually find red cars as compared to cars that are other colors. You can try to segment city streets versus rural roads and see how it does, or try to map things that are not really objects, uh, like forest canopies, and see how it does at segmenting concepts that are more textural rather than objects. So with that, maybe we can go to the poll and get folks' thoughts on how they could apply SAM3. Um, I will stop sharing here and kick these off. Um, so first question is, let's see. Oh, poll result is being shared. I'll stop sharing that. So what would you try to detect or segment with SAM3? What are you curious to detect?
You're right. I'm not sure I see a way to answer that. We
Oh, my
intended that to
bad.
be, no, we see,
Well, I'm getting one answer now. So I launched the poll. You don't see it? Oh, I'm seeing the
oh,
responses roll in.
okay.
Yeah, it's a short answer format. So um you able to see it, Phil? Now or no?
Yeah, yep.
Okay, sweet, sweet. Nice. We'll give this like, yeah, about 30 more seconds or so. Getting some good responses. Yeah, I'm just looking at the chat now. Hi, Wilfred. This is sick. We can talk to a planet. Yeah, I agree. I think it's really a really exciting direction for Earth observation as a whole that we have these sorts of models coming online. Cool. Okay. We got 14 good responses. I think I'll end the poll 10 more seconds. Someone's getting in their last response. I just saw one roll in. And okay, I'll end the poll here, and then share out the results. Let's see. Um, are you able to see the shared results? I don't see them.
I was able to see when I clicked on view details, but not sure if everyone
Nice.
did.
Do you want to read them out if you can see them? I can't see them on my end. First time using this feature of Zoom.
Yeah, I'll read a couple. So the first one was, could it possibly detect stressed vegetation or other variations just by looking at it?
Cool.
Some questions about what's changed or for emergency response, residential boating docks,
Mm,
natural hazard images, destroyed houses, fire extent. So
gotcha.
lots of good input here.
Yeah, totally. Yeah, so I think with some of these categories, you might need to detect a feature that is like correlated with some of these things, like destroyed buildings. Um, Maybe Sam could detect roofs of a certain color that are associated with like destroyed buildings. Um, but yeah, just talking about like the SAM 3 model as it is without any fine tuning, I expect it to have some trouble with like a specific category, like dis if you just tried to prompt with destroyed buildings. Similarly with stressed vegetation, um, I think SAM 3, it doesn't have the ability to handle other spectral bands besides RGB. And so I think it would have trouble with that particular category. But there are other categories related to vegetation that I think it could pick out, like counting tree crowns, at least localizing where trees are. I think it could do a good job at. With burn scars, I'm not sure. I think that would be really interesting to try. Um, yeah, really good ideas though. Okay, and I'll stop sharing this one and we'll go to the next question. Let's launch this. So yeah, what's your main interest in running SAM3 on Earth observation imagery? What are some use cases? All right, so I'll give this a minute. A lot of responses rolling in. Cool. And yeah, I think we'll end the poll here and share these out. So yeah, I'm seeing that there's a lot of interest in change detection, monitoring and change detection over time, uh, which makes a lot of sense. It's like one of the primary use cases in general for EO imagery. Uh, just to touch on that a bit, as I said before, every detection with SAM3 um, gets a timestamp. And so, and this is also the same for any semantic segmentation detections or regression detections you run with RasterFlow. And so, uh, there's many definitions of change detection, but one definition is like you can run SAM3 for particular timestamps and measure objects, that are present 1 month and then you can run the same detection next month. And then you can run an intersection with WherobotDB to see what objects are still there from month to month. So that's one definition that could be satisfied with RasterFlow plus WherobotDB. We also have we have more support for other definitions of change detection. Like if you have a model that takes in multiple time steps, um, we can run that. So, for example, we can run the Fields of the World model, which takes in a planting season and a harvest season as an array that's shaped as XY band, where the band dimension has bands from multiple time steps. And that model directly predicts fields, but you could imagine passing in a model that predicts a measure of change as well. And we're continuing to bring on support for other definitions of change detection, like maybe you want to pass in a multi-time step time series, and you have a different array shape, like you have an array that's shaped like time band XY. Um, and so yeah, we're very eager to support all the different definitions of change detection folks have. So get in touch if there's any interest here in a particular definition, and um, and we can see if we can support it today or if we can bring on support for it. There's other interest here noted, like yeah, production pipelines versus research and experimentation, and also one-off analysis and reporting. Um, so yeah, all good stuff.
Maybe Ryan, just to add one thing we didn't show today, but you can anything Ryan showed, all those workflows that you kicked off in the context of a notebook can be automated in the context of a job. So we have a job API. You can basically just submit those same workflows as recurring jobs based on your scheduled needs.
Yeah, for sure. Cool. And then maybe just one last question to wrap up. And then if folks have questions, yeah, I'm going to be on if folks want to ask those. So this is yeah, roughly how large or what are your typical areas of interest for analysis or inference? We're trying to get an understanding of where do folks um, whether you're doing one-off analysis reporting or just trying to experiment or trying to use SAM3 in production. Um, yeah, what are the scales that you want to apply, Sam? And we'll give this about 30 more seconds. Cool. Um, so I'm seeing that there's about five folks interested in small city neighborhood scale, um, but also others that are interested in, states or country scale or beyond. Um, and yeah, definitely a spread of interest here in terms of scale. Um, if anyone's feeling brave and wants to share, anyone have a share want to share like what their use case is for Sam across any of these options?
Maybe while we're waiting for that, Ryan, just one thing to make sure everyone's aware. Right, Rasterflow is currently in private preview, but let us know. Reach out if you're interested in signing up, and we can onboard you and provide free credits to help you try out Rasterflow. And also, everything Ryan showed today, we have solution notebooks. So you can basically run SAM3 straight away. There's a solution notebook. It has a default prompt in there, but if you want to change the prompt or change the area of interest, you just make those changes and you can run the notebook and test this out yourself.
Cool. I see a comment from Wilfred. Thanks, Wilfred. Yeah, for example, a utility could monitor change in its corridors or beside them. Yeah, totally. if you have high enough res imagery, like maybe you can measure changes to power lines, uh, or building structures around utility corridors for sure. Yeah, there can be a quality check of formal record keeping about activity in and besides corridors. Yeah, for sure. Cool. Well, I'll stop sharing out these results here. Um, yeah, I want to say thank you to everyone for attending, and I'll just open it up to questions if folks have them about the SAM3 model, about RasterFlow, whether it's about our mosaic building capabilities or running inference with this model, or any other models we support. Seeing some comments in the chat. Thanks everyone. Yeah. Cool. Well, if there's no questions, yeah, I appreciate all the interest in the chat and thanks so much for attending. As Phil said, feel free to get in touch. We have what's the email, Phil? Support at Wherobots, or is
That's
there a
right. Yeah.
better? Okay, cool. Yeah. So support at wherobots.com if you want to email us, get in touch. You can find our website. Um, yeah.
Yeah. And I also mentioned we're planning a regular series of these webinars. So likely one next month. We're still finalizing the details, but given the interest, we'll likely do it on change detection. So staying tuned for the next one here.
Oh, there is one question I want to get to here. Is there restrictions with world zones? Um, we're can you speak to our availability in Europe, Phil?
Yes. So right now, currently RasterFlow itself, in terms of the compute for RasterFlow, is available in US West 2. If you have a strong need and that doesn't work for you, want to run it in a European region, let us know. We can talk about that. It's generally not too much of an issue for us to spin up new regions as needed. The other dimension here would be imagery access, right? So Ryan was showing specifically with high resolution imagery that's available in the US through the USDA program. We have Sentinel-2, which of course has worldwide coverage for including Europe. And then there would be probably other open data sets that we could look at working with if you high resolution data sets in Europe, if you're interested, that we could bring in through our bring your own raster pathway.
Right. And just to highlight, like I showed this before, but want to make sure we get this. This predict or this mosaic build step is very flexible. This does not have to be like NAIP imagery only available in the US. You can index any cogs you want in a simple geodata frame, whether it's from Airbus or Vantor or other high-res imagery providers, or you can index any cogs. It doesn't have to be high-res imagery. And then once it's indexed, you pass that to build GTI Mosaic. You give your AOI, you label the bands and the cogs that you want to go into the mosaic, and and we build that. So this is really building mosaic from your own imagery, as long as you have bucket access, which WherobotDB supports storage integrations, so you can bring your own bucket. We can easily support you bringing in your own imagery, even if it's not like in an open data bucket like NAIP is. Cool. Um, yeah, yeah, for sure. No problem. Any other questions in the chat? Cool. Okay. Well, yeah, thanks everybody. I think maybe we can close it out here, Phil. Yeah, looking forward to the next one.
Yeah. Thanks everyone for attending. Talk soon.
I see one question from Wilfred that I'll answer. Do you guys make most money from the intelligence community like all geospatial companies? Um, Mostly from enterprises, Wilfred. Yeah, cool. Yeah, feel free to connect on LinkedIn, Twitter, etc. Or support at whereabouts.com if you have any follow-up questions. See ya.